It's a real pleasure to invite Linda Carpenter back to Yale, back to her home turf, where she began her career before moving up to Brown. Before I introduce her, I'd like to just highlight a couple things. One is our upcoming Grand Rounds, which is next week is Kamara Phyllis Jones, who's coming from Morehouse School of Medicine, who's going to talk about achieving health equity, tools for naming and addressing the impacts of racism on health. That should be really interesting. And then the following week, the 1st of March, at least for me, is a special treat. That is my brother, Andrew Crystal, who's Deputy Chair for Research at UCSF in the Department of Psychiatry, will be coming to give a lecture, hopefully on anhedonia, which he has conducted a landmark study on anhedonia and its treatment, which is not yet published, but which has been presented. Although I will note that the title of his talk is Insomnia, so hopefully you'll be awake during his talk on anhedonia. A couple of items, both in the news and in the department, kind of landmark moments for the department. One landmark moment was yesterday, day before? Tuesday? Time flies. The FDA Advisory Committee voted 14-4-2 against, 1 abstaining to approve esketamine as a treatment for treatment-refractory depression. In early March, the FDA will make their final ruling, but that's a strong endorsement to the FDA for the approval of ketamine. And we hope that moves forward, but if it does, it really is a nice moment for our department, because ketamine treatment for depression was discovered here. The mechanisms of the under molecular biology of how ketamine works in the brain, that was worked out here in many ways, and use of learning about how to use ketamine in treatment was worked out in Jerry's clinic at Yale New Haven Hospital. So it's really wonderful to think that the things we do academically can change clinical practice, and extremely rewarding for us, anyone who's been working in that area, to see that move forward. So that's an exciting piece of news. Another epic moment for our department was celebrated yesterday. Yesterday evening, we had a retirement party for Steve Southwick. There you see myself, Steve Southwick, and Dennis Charney. Dennis is now the dean of the Icahn School of Medicine, and he gave some wonderful comments at the retirement party. I like to think that when I was commenting about Steve's retirement, I remembered that I go so far back with Steve that he remembers me when I had a full head of hair and a beard, and I remember him when he looked exactly like he looks now. But some of you might wonder what I'm talking about. So I thought I would show that. Here's a picture from 1989. Some of you may not even have been born yet. I don't know. We are. This was right after the founding of the National Center for Post-Traumatic Stress Disorder, and we are in Moscow, late Gorbachev, and we were supposed to be presenting to people concerned about the psychiatric casualties of Chernobyl, but it turned out that the room was full of Soviet army officers, because the problem that they were really interested were the psychiatric casualties for the Soviet invasion of Afghanistan. Very, very interesting time. And so I would just say that one of the things that resonates with me about thinking about Steve's retirement and Linda's presentation today is one of the great gifts that we have in academia are the professional relationships that we develop and the experiences that we share in scientific discovery, facing the obstacles and challenges and disappointments together, the opportunity to help support each other through those challenges. If Steve was here today, he'd probably say something about the way these relationships make us resilient to the disappointments and give us the strength that we need to make the advances in the treatment, in understanding of mental illness that enable our field to move forward and ultimately alleviate the burden of mental illness. So for many of us, Steve's retirement is a landmark moment for the department, and it's wonderful to acknowledge that. So back to the grand rounds today, and it's really just an incredible pleasure to have Linda Carpenter come down from Brown. She is a real pioneer, not only a pioneer in research, but a pioneer in terms of advancing the education and research training of young investigators. She's a wonderful mentor. She's been a leading figure in our national professional societies, and let me just say about that. But I think I know the secret to her success, and it's this. Why Kellogg's Corn Flakes, you might ask, legitimately. The answer is that Kellogg's Corn Flakes come from a kind of a small town in Michigan called Battle Creek. And yeah, that's right. And all of us from Michigan always, that's right, we all, let's see.
Yeah,
there we go. It's all a matter of perspective. We always talk about the Lower Peninsula from the map of our hand. So Battle Creek is right about there, as Linda points out. So there's a small but hardy cohort of psychiatrists, psychiatric researchers who come from Michigan. Carol Tamiga comes from Holland, Michigan. Yeah, Larry Price from the Detroit area. I come from the Detroit area. A number of other people. But Battle Creek is a special place because Corn Flakes was actually developed as a health treatment to help people to get healthy and to be strong and resilient and have the get up and go to do what needs to be done. And so that's where Linda comes from. And so it's no wonder she's resilient. She went to the University of Michigan, then did a postbac at Pittsburgh, graduated from the University of Pennsylvania School of Medicine, then came to us and was in the NRTP track of the residency and completed fellowship here. One of the testimonies to Linda's resilience was this incredible study which she conducted, in which she put indwelling CSF catheters in people and sampled CSF periodically throughout the day. And this is really challenging both for the subject and the investigator. It requires a lot of support, hard to do, but it yielded a really important insight, which was that a drink that contains amino acids but not tryptophan, when consumed, lowers your CSF level of tryptophan, and in so doing reduces the turnover of serotonin, which was really important to a lot of research on serotonin at that time, which used tryptophan depletion as a strategy to try to reduce the function of the serotonin system. And Linda's work remains a seminal contribution to that literature. She did other things, of course, but this is one that I thought was particularly novel. She left us and went on to one of the great clinical institutions in the country, Butler Hospital in Brown University. Butler Hospital is this beautiful Frederick Law Olmsted. If some of you know he's the fellow who designed Central Park, McLean, parts of the McLean campus, Institute of Living, Cornell Westchester, probably some other psychiatric campuses, and she was recruited there by Larry Price, who was, as I mentioned, an alumnus of the department, former faculty member here, and Steve Rasmussen, also a graduate of the department. Steve was chair, and Larry was head of psychiatry at Butler, and I think head of research also. And they really created a Yale satellite in Rhode Island, which has had a real impact on the field. And Linda, in going to Brown and Butler, struck out in a new direction, which has turned out to be very impactful as well. That is the area of transcranial magnetic stimulation, and I'm not going to go into detail, but just to say that she rapidly emerged as really one of the leading scientists in this field, and helping to develop this as a major treatment area. As I mentioned, she's very involved at the national level. She's on the has been on the Society of Biological Psychiatry Council, the American Psychiatric Association Research Council, and played a particularly important role in advancing education through her role on the SOBP Education Committee and the ACNP, American College of Neuroscience and Psychiatry. I think that's the name. It used to be the American College of Neuropsychopharmacology, and people who made fun of it called it the American College of Narcissistic Psychiatrists. But these groups, these education committees, which now work somewhat in concert with each other, really created a mechanism for engaging people in their fellowship in early faculty years in the professional society to help them to see their futures and opportunities, to get additional mentorship and to get exposure to the field, and Linda's contributions were seminal in those areas. And so obviously she's had other roles as well. And she's received many, many honors. I'm not going to list them all, but I will say that for her, as for many leading figures in the field, the initial honor which kick-started her career was the Seymour Lustman Research Prize, which is the resident research prize in our department. And then she went on to get many, many other important honors. And I would say honors not only for her research, but also for her role as a teacher and mentor. So I could go on all day, but I promised to give her at least an hour for her presentation. So I will end my introduction there and welcome to the podium Linda Carpenter. Thank you.
Wow, that's quite an introduction. I think you prepared more for your talk than I did, perhaps. I also feel like I've been a little Google stalked, where all those pictures came from. But I do want to say something about Battle Creek, Michigan, and it's true that Kellogg's was founded there, started there, and when you grew up in Battle Creek, which is a small town, there was also Purina is also headquartered there. So you had Kellogg's cornflakes cooking at one end and Purina dog chow and all the other chows at the other end. And no matter where you stood, there was a smell of corn in the air. You didn't know if you were smelling cornflakes or dog kibble, but it was definitely a corny town to be in. Okay, so now I'm going to try to find my presentation, which I obliterated so that we could. Here we are. Thank you for inviting me back here. It's such a delight to come back. Dr. Sanacora toured me up through the CNRU, where I sat 22 or so years ago, and it really doesn't look any different. The office that I was in is formerly a closet, is still for somebody's closet, and but wonderful things happen here despite the nicks and the scratches on the walls. I'm very excited to talk to you about transcranial magnetic stimulation therapy. And when John was talking about all the fabulous discoveries that have happened here with regard to ketamine and its glutamatergic actions, I was thinking that Rob Berman and colleagues here were doing transcranial magnetic stimulation therapy many, many years before it was ever FDA approved. So I think that some of that seminal, maybe seminal or beginning work was done here. So here are my disclosures, and I think of most relevance to what I'm going to talk about today, I have a line and a dot, okay, is that I have some funding from companies that make TMS devices, including Neuronetics and Neosync, which makes a device that's investigational, a lab with a company with a very unfortunate name called Feel More Labs, which are trying to get in. And I have equipment, TMS equipment from a few companies as well. And I consult to MagStem, who's also a TMS device manufacturer. So I'm going to talk a little bit about TMS for depressive disorder. And I want to say, I have to apologize too. Jerry let me know yesterday that the last 2 grand round speakers, or 2 in the last couple of months, have been neuromodulation topics. And I imagine you're fully saturated after hearing Dr. Lisenby and Dr. Nolan talk about this, but I will try to keep my talk today quite clinical, and I do have to comment that this clinical service, TMS therapy, which has been FDA approved and really out in the clinical community for over a decade now, has not really taken off in the Yale affiliated clinical programs. So I'm hoping that I really inspire and jumpstart some great stuff going on here. I'll talk a little bit about the new developments outside of depression and neuroimaging and EEG biomarkers, and then what do we think TMS is going to look like for the future. So you probably got some good background when Nolan was here, but people have been doing a version of TMS for many, many years. Electromagnetic stimulation being demonstrated here in 1896, and here the first time applied to the head, where the professor Sylvanus was doing retinal stimulation and generating magnetophosphines, which are little spots that you can see in your eye when you stimulate occipital cortex. Mike Poulsen in UK, who I know and am very friendly with now, he's first created the peripheral nerve stimulator with the technology which eventually was applied to the top of somebody's head by Professor Tony Barker in England, and that was in 1985, not that long ago. These 3 in the UK made the first transcranial magnetic stimulation device to apply to somebody's head. And magnetic energy, unlike electricity, goes through your scalp and skull unimpeded. So you can point here and deliver stimulation there, unlike electricity. And when you do ECT, of course, you're applying electricity through electrodes, and it travels through your skin and tissues, through the cranium and the skull, and then depolarizes neurons in a fashion that's a little bit more random. This is a little more focal. I don't want to over-exaggerate how focal it is, because magnetic energy spreads and it doesn't go terribly deeply into the cortex. But here's the concept. And it would probably be cool if I could get a dot out of this, but nevertheless, you've got a coil of wires, or a coil of something that conducts electricity, right? And you're going to shoot electricity through it in a pulsed way. And Faraday's law of physics tells us that when you pulse a magnetic field, you will induce current in a perpendicular plane if you have a conductor there, right? So here's the coil, and here's the magnetic energy, and you can induce a current in that direction. And it turns out, of course, that our brains are full of tissues that conduct electricity, like cortical neurons. And so it penetrates your scalp and your skull there and depolarizes neurons, and you stimulate, of course, in one particular spot, only a couple centimeters below the cortex, but because we're wired in circuits, you get activities and changes in the brain, not only right underneath the coil, but in more distal regions, and I'll talk some about that. This is just simply how the energy transfer goes, and you've got a time-varying electrical force coming through this coil, and it's making a time-varying or a pulsed magnetic field that's inducing current. And here you see we're going from the coil's current to the magnetic field pulse and the rate of change, and you can see the reciprocal relationships between those. There we have induced current, and that's now we're in cortical tissue. Here we're going through the skull and cortical tissue, and at the bottom, behavioral change. The way TMS works, and you probably got a little bit of this background, is that we have to calibrate the treatment according to, or maybe we don't have to, but we assume we do, to the level of excitability of each individual brain. So we do this by starting off and delivering pulses, single pulses, to the motor cortex. So if you remember the homunculus here, which is the man mapped out in your primary motor cortex, which is here in that red strip. So in between my ears, I can take a coil and put a pulse here and keep turning it up, and turning up until I have enough to cause an action potential in a cortical neuron, which through its cortical spinal tracts will cause a twitch in the contralateral hand, right? And then if I turn it down, weaker pulse, that disappears. I can turn it back up, and I get the twitch again. And we get that a value, which we call your individualized cortical motor threshold. And then the whole treatment is calibrated against that, which means that we assume no matter where we stimulate in the brain that it's all going to be as excitable as it was in your motor strip. Now you may challenge whether that's a reasonable assumption, but that's nevertheless the way the treatment is delivered. And that's an important safety feature of TMS because some people will have a very low motor threshold. Say you've had a huge amount of coffee and a couple Adderall and you haven't slept, you come in, it doesn't take much magnetic energy to cause an action potential, which we can see in a twitch. If you come in, you're taking a bunch of anticonvulsants and benzos, or maybe you're just somebody with a high motor threshold, it takes a whole lot of energy much more to pulse to get one of those neurons to fire. So if, say you had somebody with a very low motor threshold and you're delivering something with a very high intensity, too high, not individually calibrated toward their brain, you could potentially induce a seizure, right? So if you are stimulating and propagating the depolarization and action potentials in neurons heading toward the motor strip, then you could actually cause a seizure. And that's one of the side effects or the potential risks, not a side effect, a potential risks associated with TMS therapy. Turns out that it's much less common and the treatment's much more safe than we thought at the beginning. But we do not want to be inducing seizures with TMS unless you're in Holly Lisenby's group, in which case you are absolutely wanting to do that. But here's the setup. Now, I'm not going to take a lot of time and walk you through a lot of clinical trials data because there's so much else. It's been a decade. It's been a decade that we've had FDA-approved TMS devices for depression, and there's so much more to talk about that's very interesting than to really walk through the first two clinical trials. But basically, in the clinical domain, all of the devices that are approved fall into one or two categories. You either have a figure-8 coil, and the first company that did this, and I'm not trying to be biased, but I'm just going to have to give you some company names to put things in context, was Neuronetics. And they had a large-scale, multi-center clinical trial with medication-free patients who were treatment-resistant, and they had failed to get better with multiple medications. And they had to pick a set of parameters, which they had developed in the years leading up to this. This would have been prior to about 2000, year 2000. And so they picked 3,000 pulses to the left dorsolateral prefrontal cortex and the trains that were 4 seconds long, like a logo, tap, 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 tap for 4 seconds, and then it rests for 26 seconds. And it comes back, tap, 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 tap for 4 seconds like that. And so that whole session with 3,000 pulses, and it takes 37 minutes, and people would come 5 days a week for 6 weeks, and then at the end of 6 weeks, they'd taper, 3 1 week, 2 treatments the next week, and then 1. And then another company, a second company that came along, had a very different kind of a model. Instead of a figure-8 winding of the coil, it's in this very kind of complex and large arrangement, which is called the H coil, or Hersed coil. And this company, which was called Brainsway, developed these coils, and they came out and did a large-scale clinical trial with treatment-resistant depressed patients who were medication-free, a regulatory trial, and they pulsed a little different. Also high frequency, 18 pulses per second, but a little less than 2,000 pulses a day, and they had a slightly different train. We talk about trains, how many pulses are grouped together with a space in between them. And they treated for 4 weeks at 5 days a week, and then they started to taper and did 2 a week after that. So every other device that came in was either that company, and there's just one of those, or this. And there have been 6 others that subsequently got FDA approval, not by doing their own clinical trials, but just by showing that their device is technologically equivalent to this one that already did the clinical trials. So when they map on, they have all these parameters they have to adopt. And if you have this device, those are the parameters that you have to adopt. So insurance coverage for now in the world of depression is in place. All insurance carriers, commercial, Medicare, Medicaid, cover it for unipolar, non-psychotic major depressive disorder. You have to have failed multiple antidepressant trials. Some insurance policies require 1, some require 4, or you can be treatment intolerant, because we know many of our patients will try to take medications and develop side effects, so they can't get to an adequate dose for 6 or 8 weeks. And everyone has to have failed a trial of psychotherapy. So the clinical trial that Neuronetics did, testing their device, used a week 6 Montgomery-Åsberg Depression Rating Scale, these as well as at baseline, week 2, week 4, week 6. And they had a 24 versus 13% response rate. And the primary outcome that they had designated ahead of time to the FDA was their Hamilton Rating Scale. And at their study endpoint, the difference between active and sham groups was p equals 0.058. Which is any scientist's nightmare or researcher's nightmare, right? Because they had specified it would be less than 0.05. So the FDA worked with them and said, hey, all your secondary measures are positive, your MADRS was positive, but that wasn't the one you picked. How do we sort that out? And together they came up with a subset of their sample, which was about half of the sample who had failed 1 adequate antidepressant trial, even though they may have tried, I think, up to 24, only one of them met adequacy criteria. And there they had much better outcomes and much more significant difference between active and sham, about a 50% response rate and a 33% remission rate. And after they finished that trial, then NIH, the Institutes of Health, sponsored another trial with the same device. And this one, the company had no role in other than to give the devices to 5 academic centers. And they did a study called OpTMS. They used the same parameters, the same devices, and they were able to replicate that finding that Neuronetics had. And so those data and those parameters apply to all figure-8 devices. Everyone that has a figure-8 coil attached to it, that's the FDA label that goes with them. And then Brainsway, in their clinical trial, their primary outcome was the week 5 Hamilton scale, and they had a 38 versus 21% response between active and sham, 33 versus 15 in remission. And their coil, which I'll show you in a minute, which is very different, instead of just very focally stimulating the left dorsolateral prefrontal cortex, it's got these windings all over. So you're really stimulating both left and right prefrontal cortices, mostly left, but also some right. And that's what their device looks like. It's in a helmet like that. And this is what the Neuronetics device looks like. Here are all the others, and every single one of these came through the FDA regulatory pathway of the 510K, which means they didn't do their own clinical trials, except for this one. And this one, that's the only figure-8 coil. The only H coil, and that's in the helmet here. You can see all the rest of these are figure-8s. And really, these devices basically have a coil, some stimulators that deliver the electrical energy, and sometimes a chair and a computer interface. So the things that have created potential and have already started to differentiate here are many with TMS. And I think this is a little bit different than pharmacotherapy because there are so many energy parameters. There's so many different places that you can put the coil on a person's head, depending on what circuit or what node or what region of the brain you want to stimulate. You can stimulate with very high frequency, which is excitatory to neuronal activity, or very slow, 1 pulse per second, which is inhibitory. Right? So if you wanted to dampen or turn down activity in a circuit, you could stimulate at 1 hertz or less. You can do multiple sessions per day, and these are questions: can we get people better faster if we just pile a bunch of sessions on? Do we need some time in between them? How does it work? We don't know how it works. People often get excited about that and say, well, we don't know how TMS works. And I say, well, I don't know how Prozac works, and I don't think we know how EZT works or psychotherapy. So we still have a lot to learn about all of our treatments. We know certainly where their immediate, sort of mechanisms of action are, but then after that, how they work to relieve symptoms, I think, is still a black hole. So one of the most exciting areas to add to all of this is, what are you doing when your brain is getting stimulated? A huge body of basic psychology and electrophysiology work has shown that combining endogenous neural activity with stimulation, you get better traction, a better learning, and you can facilitate effects. There's long-term potentiation or long-term depression, depending on what type of stimulation you're doing. So the opportunity to put together stimulation with something else that you would want to use, like some sort of therapy to affect a change, is a great potential for us with TMS, and I'll talk a little bit about that, particularly with regard to OCD. So So first there's this coil geometry thing. Remember I said that the first one that did was a figure 8 coil, and in fact it was this one here. These are models, and each one shows the coil on the left side, and then on your right side is a model of the induced current, the E field in the brain. So you can see there's sort of a small red spot there, right? That's where it's really focal, and then it's not very big or very deep. And then all of these are figure 8 coils, some of the other ones that I showed you, and they all have kind of that same profile. The H coils, on the other hand, the ones that Brainsway put together, are this row up here, and you can see that there's a much larger area of red, so they're stimulating a much broader area of cortex, like huge. You're just kind of blowing the whole front of your head there with stimulation-inducing current. So a question that you might wonder is like, well, do you want to be focal and go to a specific spot, or do you want to get a whole lot of cortical tissue stimulated? And the answer is we really don't know. What we do know is that this is not a laser. You can't go deep without going broad. So if you want to get deeper into cortical tissue with TMS, you have to go broader. There's no way, because of the way magnetic energy falls off. So this is just a figure here that shows the trade-off between the spread and the depth. There really, other than using these very complicated coils or multiple coils in an array, it's very hard to get deep into cortical tissue. So this company, Brainsway, who had the H coil for depression, recently moved forward with a new indication, a new coil, also another one with very complex windings on it, and got FDA approval for treating OCD just a couple months ago, actually. And their hypothesis is that they wanted to reach anterior cingulate cortex. And they had thought that that was a good target because there were some fMRI findings showing that patients with OCD had abnormalities in the anterior cingulate, and that the volume of the anterior cingulate was decreased in patients. So they developed this coil. These are what the windings are like here, and modeled it to convince people that they were able to stimulate deep enough to hit anterior cingulate cortex. They did something also that was quite innovative for TMS, because the regular body of work for TMS therapy for depression does not require that the patient do anything in particular while they're getting treatment. They drive themselves in, they sit in kind of reclined chair, the coil's put on their head. You either wear earplugs or earbuds and listen to some music. Some clinics have a video or a TV playing, but it's really not tied to any other sort of activity. But what they did here is they had a randomized controlled trial, and they combined an exposure trigger with the stimulation. And this is how they did that. They had outpatients who were, and again, all of these treatments have evolved in outpatients. They're all FDA covered for outpatients. They have not yet been FDA approved or extensively tested in inpatients, which doesn't make a lot of sense, except for it does take 6 weeks of daily treatments to get people better, and that might not fit with the modern model of inpatient care, which is where I practice about average of 7 days. 7 to 10 days. So these are patients who had at least moderate OCD using the Y-box, and they were able to stay on their SSRI medications. The previous depression trials took patients off, but they allowed them to stay on if they were approved for treatment of OCD, and if they were undergoing some psychotherapy, some CBT, exposure response prevention, they were able to continue that. And this is the characteristics of the sample here. And they treated them with this H-coil transcranial magnetic stimulation after a lead-in period. And what they did first is they sat down with every patient before they started the study, and they did a Y-box and figured out what what would be triggering for them, what would be symptom-provoking for them. And they listed all their obsessional thoughts and their compulsive behaviors, and they picked ones that were going to activate at least a moderate level of severity. And so they developed some scripts or some props that they could use, and they could have been internal provocations, like someone would ask them questions that would get the OC symptoms going, that would typically trigger them to do some compulsive behaviors, or they could be some external provocations by using some photos or having the patient do something. If they had obsessions and compulsions around cleanliness, maybe it would be touch the floor or touch something dirty immediately prior to the treatment. And so they exposed them for a period to about 5 minutes, and then they stuck them in the device and put the stimulator on and stimulated the anterior cortex. And they treated over 6 weeks, as you see here, active or sham. And Again, as a typical study would go for TMS, there's a period of screening and then randomization, and then the assessments at a regular interval, typically a week or one or 2 weeks. And they treated through 6 weeks and then followed up at 10, 11 sites. And they randomized these subjects, and they were successful in demonstrating, this is the protocol that they use, 20 hertz treatment. Now this is, you might think, quite unusual, because I would imagine if I were designing their study that you would want to provoke the symptoms and then use stimulation to inhibit activity of the targeted circuits. But they did a pilot trial where they used slow stimulation 1 hertz and fast stimulation at 20 hertz. And they did that for a while, and they noticed that the 20 hertz, it was randomized also with a sham component, and they realized that the higher frequency was working better. So they went on with that 20 hertz treatment at 100% of the resting motor threshold. And for this, because they're stimulating quite medially, instead of doing a pulse and looking for a twitch in your finger, now you're over the area of the homunculus that's going to cause a twitch in your toe. So they had to calibrate according to the cortical excitability at that level, so that they could properly calibrate the treatment. And these were about 18-minute treatments apiece after 5 minutes of the symptom provocation. And here are their outcomes that led to FDA approval. For OCD, typical clinical trial outcomes are a little bit different. In depression, we call 50% reduction on the scale a response, and then a score below a certain threshold is called remission, and we've all agreed on what those remission scores are and these definitions. For OCD, a response rate is about a 30% reduction in your Y-box total score. So here we have the active and sham conditions compared. And then they have another outcome which they call a partial response rate, which is a reduction of about at least 20% in the Y-box scale. And I think that there really aren't any treatments that drive home a big response in OCD. The nature of the illness being what it is, people consider this a very good clinical outcome. And as a result of this, FDA approved them for the treatment of OCD. The number needed to treat in their trial was 3.7, which means you need to treat approximately 4 patients before you'd see 3.7 patients before you would see a patient who benefited, and this was well received. So now we have depression, we have OCD. There isn't yet in place insurance coverage and a lot of sort of structure about how the OCD is going to play out. It's just freshly FDA approved. But another advance in the field is neuronavigation. So right now, when we go to treat patients, for depression at least, you find that motor hotspot, which is somewhere between the ears, right? And then, this is the way Neuronetics did it for their trials, then you just measure 5 centimeters forward. So if I find in between my ears here, here's my twitch, then you measure 5 centimeters forward, that's where you'd place the coil to treat for depression. Well, that's absurd, you should say, because some people have big honking heads like this, and other people have little heads like that, and 5 centimeters in a small head might, put you over the eyebrow, and in a big head might not put you very much toward prefrontal cortex. Another way that people have been targeting the dorsolateral prefrontal cortex, which is where all the figure-8 coils treat for depression, is by using EEG coordinates. And there you measure the head, you assume it's a perfect sphere until you get a vertex, and then you can find a spot where you would put the EEG electrode if you were doing electroencephalography for F3. And some people do that. It's probably a little bit better because it's scaled to the size of your head. But what would be really cool is if you could get a person's individual brain and know exactly where you're stimulating in there, right? So neuronavigation systems do exactly that. You take an MRI, a lot of slices of the person's brain, upload it into the equipment, and now in 3D space you can play with it. You can peel down, you can slice it, you can revolve it, you can see all your anatomy. And there you can use any variety of different ways to target where you want to stimulate. And then when you put the coil on, you've got a coil and that's got a sensor on it, and a person who's got a sensor on it. And then there's a camera up here. Now in 3D space, as you're watching your screen of this person's brain, you can see exactly where you're going. And with good modeling in these systems, you can see exactly the trajectory and what you're going to stimulate in an individual person's brain. There is a system called Neuronics, which, NextStim. And they've had this device on the market for many years to do pre-surgical mapping. If you had a tumor in your brain, they could use this in a very precise way to figure out what functions were going to be impacted by surgical resection of a tumor. So they went to FDA and got approval for treatment of depression. And that's fabulous, except for we really don't know exactly where we want to go, right? So the million-dollar question is, okay, now I can figure out exactly where in your brain to point and to stimulate. I can either inhibit it or I can excite it, but where should I go? And a large body of treatment has either stimulated the front of the head or the left dorsolateral prefrontal cortex. For sure, now we can go into your individual brain and anatomically find, okay, there's the spot I want right there in that middle anterior gyrus. But it's not clear that that's the best spot, right? And you might want to put somebody in an fMRI scanner, and have them do some particular task where you're lighting up a particular circuit. Then you can upload that, overlay it, and really specifically go to a spot that's customized for a particular brain. But some time ago, this is back in 2009, there was a question about whether if you neuronavigated it versus just measure 5 centimeters, would you get a better antidepressant outcome? And Paul Fitzgerald did a study where he randomized people to either standard treatment or targeted treatment, and targeted meant with the neuronavigation. And there was some suggestion that the outcomes were better. There were 42 versus 18% responders, but it wasn't really fully significant. It maybe wasn't powered well enough. This is 51 patients who got 4 weeks of treatment. But that's the only real data that our field has had, and it wasn't good enough. So, of course, the insurance companies don't pay for everybody to get a $1,000 or $2,000 MRI before they get a course of TMS therapy. And we still are using some of those cruder methods, unless, of course, you're in a research clinic or you're in a specialty clinic in California where you pay $2,000 to get your MRI. There's a huge body of work now that's trying to help us answer this question. Where should we put the coil? What are the circuits we want to stimulate? How do we make TMS do the best thing that it can for people? And these come largely from imaging studies, to a lesser extent from some EEG studies, but some of the most important work has been done by a group in Stanford. And Connor Liston and his group really helped us along by doing fMRI of patients before their first TMS and then after their last. And really comparing those two pre and post treatment, they could ask what has changed in connectivity, looking at functional connectivity, and what has changed that goes along with an antidepressant response with TMS. And there is work, and a number of other people's work point to subgenual anterior cingulate as critical, and they looked at that and its relationship to activity of the default mode network, which you may know is the network that's active when we're kind of offline, not doing much of anything. And they are able to find that connectivity at baseline of the subgenual with various of these nodes predicted better response to TMS therapy. So in the blue bars here, you've got a strong TMS response over ventromedial PFC, orbitofrontal cortex, and anterior cingulate and dorsomedial prefrontal cortex. Whereas the little green bars you see here are patients who had weak TMS responses. They didn't do as well. They're in the lower median of response and change. And so they've been able to start to give us some predictors with regard to connectivity and some ideas about what changes. Another study similarly did imaging before and after TMS, and again created more evidence that anterior cingulate cortex is key. Here they found that what changed during TMS was increased connectivity of the subgenual anterior cortex to the dorsomedial prefrontal cortex, and that treatment was also associated with some changes from subgenual to other areas, insula and striatum. So and there's a huge body of work, and I don't want to bore you all with many, many imaging studies, but they're really starting to take us toward some understanding of what are critical, at least regions for connectivity analyses in predicting TMS and what is changing with TMS. It would be great if all these studies were similarly done in studies where patients were randomized to a pharmacotherapy intervention or ECT or ketamine or something like that. We might be able to then glean whether these are specific to transcranial magnetic stimulation or whether they're just associated with antidepressant response. But the beauty of having these sorts of studies is that you can compare what changes pre-post TMS, even if it's unrelated to the symptom improvement. This is a body of work by Mike Fox and colleagues and weekend at Beth Israel Deaconess Medical Center. And using a human connectome map, which is made from a normalized map from 1,000 brains, they can make estimates for how well somebody will respond to the treatment based on where the coil was placed and its connectivity to subgenual anterior cingulate. So when I say where, everyone thinks they're going to the dorsolateral prefrontal cortex, right? We all, one way or another, either 5 centimeters or the EEG measures, everyone thinks they're going there. But of course, we're not all mapped exactly the same. Our brains are individually different. And so using the connectivity map, they're predicting that where you hit that node on the head and its relationship to subgeneral is critical for getting better. And these are studies all in depression. And finally, there's a number of imaging studies like this one where people are put into different endophenotypes or biotypes. This is the Drysdale study, which you may be familiar with. And here they did cluster analyses of fMRI data from many, many patients, 1,188 who had depression. And they found 4 distinct resting state connectivity networks that they called 4 different biotypes. And these were data gleaned from a lot of different clinics in a lot of different ways, but they had a subset of people in this cohort, 124 who got high-frequency transcranial magnetic stimulation to the dorsomedial prefrontal cortex. And they are able to find that one particular biotype 1, I believe it is here, the circuit identified by those, which doesn't really look like it's going to hang out in your head particularly, but was more responsive than others to TMS therapy delivered that particular way. But this kind of endophenotyping work is very exciting in helping us understand, at least for a particular type of stimulation, what might be the critical pathway to get to the circuitry that's going to help us with depression. There have been, in addition to dorsolateral prefrontal cortex, a group in Canada has been very interested in this dorsomedial hub, and their idea is that this is a cortical node, and again, we can only get a couple centimeters deep with the TMS coil, so you need to find a spot that's going to connect to everything else that you think is important. Again, what everything else is important is the question that's still getting worked out, but at least it looks like activity in some of these circuits that we're getting to know in relationship to depression is important. So this is a coil that sits right there at dorsomedial prefrontal cortex, and based on these networks, these prefrontal regions that we're in PET studies show that the resting metabolic rate is different for patients with depression. There have been, different kind of hubs defined, and their interest in dorsomedial was that this is sort of a nexus, a dorsal nexus here that links the 3 networks that people have been interested in: the cognitive control network, the default mode network, which is offline, and the salience network, or the affective network. And so they did a study and delivered the TMS right there to that node that they felt was important, and had outcomes with this. This was not a sham-controlled study. They were able to show good outcomes that were better comparatively to some of the outcomes that you get when you're just treating dorsolateral or kind of randomly. But again, a large clinical trial randomized would be needed to really know. Another thing people want to know is like, well, if I want to get people better faster, what do we see in the clinic? We've got a very busy clinic. We treat maybe 16 or so treatments a day. And what we see is that it takes a couple of weeks before people get better. I don't think they get better quite as quickly as they do with ECT, for example, and certainly not as quickly as with ketamine. But maybe you're getting into the 2nd week, people are starting to get a little better. 3rd, 4th. Some people you go all the way to week 4, 5, and 6, and now they're just starting to turn the corner. In fact, some of the pivotal data that Neurodynetics did at the beginning showed that if you went all the way to 6 weeks and you had a bunch of non-responders and you just kept going daily TMS for another 6 weeks, you could convert another 1/3 of them to response. So why some people need less daily stimulation and some people need more, probably a function of their inherent plasticity. And there are some studies looking at plasticity measures in the brain and whether they predict outcome. But again, if you thought that you could do more, maybe more treatments in one day, right? So we don't know how many pulses you need, how many treatments. If you put too many together and you just sit somebody there and keep pulsing on their brain, eventually they feel kind of juiced. So some people feel that there needs to be a sleeping period in between for consolidation and the after effects on a neuronal level plasticity to happen. But people have been starting to experiment with this and wonder if you just do more sessions a day versus more sessions over time, can you get people better faster? And this is a group from Canada who put their data together. And again, this is not a properly prospective randomized trial, but they had data to try to address this question. And they did find that there was an effect on the pace that people get better. They could get better more quickly if they did 2 sessions a day. I think they put 80 minutes between the sessions of a break. But now you're talking about a treatment where somebody comes in the clinic, they sit in the device for a half hour, now they have to go hang out for an hour and a half, come back for a half hour. So that's not terribly practical. At the end of the number of weeks that they treated, 6 weeks, there were the same number of responders, but they did get some people better more quickly. One of the most exciting developments, which I think you heard Nolan Williams talk about here, is theta burst. And speaking to this issue of sitting there for hours and having to sit there for more hours, theta burst, which is a very different kind of pulse pattern, which I think he described when he was here not too long ago, has recently got FDA cleared with one of the device manufacturers for depression. And what this treatment does is reduce a protocol of stimulation, which was 37 minutes, to 3 minutes. And that could be a significant advantage. They did this, the company that got this is a Mag Venture, and they have a figure-8 coil targeting the left dorsolateral prefrontal cortex. And theta bursts, instead of pulses being individually like that, separated by a second or 10 per second, it packages together very, very rapid bursts of pulses, right? So you get 50 hertz bursts like that, and you put them on a carrier frequency, like 5 per second. So be like a theta burst. And theta, of course, is the range of EEG frequencies of brain oscillations, which vary in the range from 3 to 7 and 5 right there in the middle. If you look at EEG in everybody's brains, we have these inherent oscillatory rhythms, and alpha, which is somewhere in the area of 8 to 12 or 8 to 13 hertz. Right in the middle of that is 10 hertz, which is where a lot of these treatments do. And some people think, oh, if you're in that range, you can modulate those rhythms. But this one uses a theta frequency, so named because of its 5 hertz carrier. And they treated at a remarkably high intensity, 120% of the resting motor threshold, and gave 2 sessions, or 20 sessions over 4 weeks. That's every day for just 4 weeks. And again, when you think about these pulse patterns, I would just want to point out that the data we have to help us understand what they do to the brain are largely these sort of PET data. This is a study in depressed people that shows when you treat very fast, 20 pulses per second, you have a lot of increases in cerebral blood flow in the brain, showing metabolic activity is turned up. And many of these areas, cingulate drives, prefrontal cortex, amygdala, are areas that we think are critically involved in the circuitry of mood and anxiety disorders. And here's brains of depressed patients who were treated with 1 hertz, which we consider inhibitory. And you can see it turned down a lot of those same areas. So what we know about theta burst, so here's like a single pulse when you're like doing a motor threshold. Here's 1 hertz treatment, 1 second apart. Here's your 10 hertz treatments. And so theta bursts, now each of these pulses becomes a burst, like that. And if they're separated by some time, we call that intermittent theta bursts. And if you just give those bursts continuously, that's called continuous theta bursts. And that's got long-term depression-like effects. And all of these effects, its effects on neuronal activity with regard to LTP or LTD, are determined in studies where it's applied over the motor cortex, because there it's very easy to ascertain what its effects are on subsequent neuronal activity and firing. So a large non-inferiority trial. This is not a trial where people come in and get randomized to active or sham theta burst, but everyone comes in the door and gets TMS, and you either get randomized to active standard 10 hertz treatment according to the FDA-approved protocol, or to this theta burst. And they did have some dummy treatments so that everybody got both. Some were sham so that you didn't know, oh, mine was only 3 minutes, I got the theta burst, and mine was. So there was a 10 hertz sham or a theta burst sham, and everyone had to get both applications. And they had a large population, over 400 people randomized to either, and showed outcomes. When you look down, up and down this line, you'll see no differences. I know it's a lot of numbers, but essentially these are the different scales: the Hamilton, a self-report scale, the EDS, and the QIDS. And there's no differences. They were identical outcomes. And this was important and big enough and powered enough to establish that there was no difference between what was considered the standard of care and this new 3-minute treatment. And this is very exciting, and many people are interested in incorporating this into their clinical practice, feel like people can get in and out the door more quickly, they can treat more patients in a shorter amount of time. And so this really is somewhat revolutionary for the clinical world of TMS. A couple other developments relate to the populations we can treat. And if I had tons and tons of time, I could show you so many different studies from so many areas of neuropsychiatry where the TMS is being evaluated and as a treatment potential. There's also a whole world of sort of basic translational and physiological experiments which uses TMS to study the brain, to inhibit areas or to study plasticity as a research tool. But I'm talking today about its application as a therapy. And some of the most exciting areas are, its potential to be used in patients where pharmacotherapy or ECT are risky, like pregnant and nursing women. and or people for whom ECT is not safe because of their medical comorbidities and anesthesia isn't safe. And this is a pilot study that was done which showed a very exciting sort of preliminary effect by Garcia and colleagues a couple years ago. Since this time, Neuronetics sponsored a randomized controlled trial in postpartum depression. This is postpartum depression. And they used the lower frequency of fear for inducing seizure in women who might have an increased seizure threshold. And there have been a number of studies, I haven't mentioned this, but in addition to studies, good randomized controlled trials showing that it works when you tap on the left 10 hertz, there are also studies that show it works when you tap the right at 1 hertz for depression. And that's a particularly anxiolytic effect. If you ever get a chance to get TMS and somebody puts the coil on and taps at 1 hertz, you'll feel very calm, like you've had a Valium. It's a very anxiolytic effect. It's quite interesting, but it's also in a number of studies proven to have an antidepressant effect. And some researchers and some clinicians will go fast on the left and bring the coil over here and then go slow on the right to sort of target the anxiety and to target the depression in 2 ways. But anyway, there was a large-scale clinical trial done, which I didn't present because they haven't published it in peer review yet, but they confirmed an effect in postpartum depression and anticipate revising their FDA label so that they'll treat postpartum depression. And I think that's exciting. It's great to have some more options. Personally, as a woman who's had some babies, and if many of you men or women have had babies, getting to a clinic 5 days a week for any amount of time when you've just had a baby for the first 6 months afterward would be not the most convenient treatment one could imagine. But nevertheless, an option that wouldn't involve exposing a nursing mother to a pharmacotherapy. Those were done in women who were not on medications. And then very, very recently, just this month, a study was published with the senior author of Neil Epperson, who was my colleague and another Yale graduate from the CNRU upstairs here, who's very active in treatment of women's health. And they did a randomized study for treatment of depression in women that are pregnant. And this really needed to be done. No one wants to do studies in pregnant women. You know, we're all afraid that as researchers someday you'll get sued because Johnny didn't go to Harvard when he was, in utero during whatever investigational study you were doing. But this is such an important need in an area where people don't want to be exposing their infants or their fetuses to developing babies to pharmacotherapy and anesthesia. So they randomized people to active or sham treatment. And they also looked at changes in estradiol and progesterone, and there were none. And they had a number of other neurochemical indices that they evaluated for safety in these women. And they treated at a very kind of a weak dose of TMS, 100% motor threshold with 1 hertz and 900 pulses. This is a smallish study, 11 active, 11 sham, and women were in the 2nd and 3rd trimester. And they had response rates of 82% and 46%, and a remission rate of 27 and 19%. So that is a very positive signal, even though it's a small study. Now, to this topic of what could you be doing while a person's sitting there for 37 minutes, right? This is a great opportunity, if it were possible, to capitalize on the neuroplasticity induced by this treatment and some other treatment that would help a person, like cognitive behavior therapy or exposure response prevention, right? So what we've pilot studied in our clinic and are now working on in a more larger and significant way with a different sorts of outcomes is using behavioral activation therapy. And behavioral activation therapy is a therapy designed to help engage people in activities that promote hedonic drive, things that they once enjoyed or valued before they became depressed. And it's a very good fit with TMS because the technician has to come in and assess every day how are you doing, set them up in the device, leave them alone for 37 minutes, and then come get them on the way out. So it's easy enough to have them say, hey, why don't you set a goal for something today, something you could do, some small thing that is a step toward engaging in something you used to enjoy. You used to like read books. How about if you find a book, I'll check in with you about that tomorrow, and then check in on your way tomorrow. And people will progress their way through various goals as they're getting better and be more engaged in a number of these things. And when people ask about what you can do to sustain the benefits after TMS therapy, we really don't know. That's it's another area which is just screaming for more research, and I can take a minute and talk about that, but Certainly, the best we can do to all our patients is recommend that they do things that keep their brain healthy, right? Eat their green leafy vegetables, get some exercise, get some sunshine. But helping people, kind of coaching them through a course of TMS to engage in activities. They used to like to walk, they're walking more, they're reading some books is also something that probably helps. Probably, we don't have any data yet, but we would hypothesize helps to sustain their benefit and maybe even bring them some benefit if the TMS itself isn't working for them. Another example of combining TMS with therapy is played out in this very elegant work also that the Brainsway company did with a sort of complicated coil in a PTSD study. And this is a large randomized trial that they conduct, and they used a brief exposure therapy just prior to administering TMS. And their goal is not to facilitate or reinforce it, but they're trying to promote a fear extinction. So they're trying to trigger in the PTSD patient and then turn off that fear response and anxiety response. So they developed with all of their patients a script-driven imagery, and they assess people and their life events, and they have the patients record some audio scripts that are 30 seconds long, and they took their patients and randomized them into 3 groups. One group got the TMS after exposure to the provocation, which is again listening to these audio tape scripts of traumatic events, and then they listened to a traumatic event script, and then they immediately afterward listened to a neutral event script. So everybody had to have both sorts of scripts. Or you could get sham treatment after your exposure, and again, that would be a traumatic event script immediately followed by a neutral event script. And they also had outcomes which to further sort of bolster their finding about turning off that response to the trigger, to the trauma, by getting heart rate variability and skin conductance through their study. So the groups either had, sorry, I don't think I explained that very well, either the traumatic event and a neutral event, or a positive event and a neutral event, or they got sham with the traumatic and neutral. Everyone gets the neutral afterward. This is the coil they used, and it's kind of hard to see what's going on here, but the active coil is actually the windings in purple, and the sham coil is what was in gray. And this is all encased in a helmet, so the person can't see what's in there, and it sits down. And there's enough action in there for these shams. The things vibrate, and they kind of move around in your head, and you produce headaches and all sorts of stuff, so that it's a well-shammed study. And that's an issue inherent in a lot of TMS studies, is whether the shams have been good enough. When the Neuronetics company first did their study, and then the NIH trial came out, they introduced a very special extra step to make sure that nobody could guess whether they were getting TMS. Because when the stimulation is happening, there's all these little peripheral nerves that cause our faces to move around, right? And you can get some twitching in your face. So what they did is they put some electrodes on here, and every time the sham coil would go ch-ch-ch-ch, and the sham coils often have like a steel plate or reversed windings, so they don't actually deliver magnetic energy into your skull, but the thing's shaking, and they had these electrodes so that everything was twitching, and the patients really couldn't guess. They had optimized the sham beautifully. And so when we look at these studies, we're always a little skeptical about whether it's a good enough sham. So for this PTSD study, they did 3 sessions a week times 4 weeks. They did high-frequency stimulation, 120% motor threshold, and their target was really medial prefrontal cortex. But these are huge coils, and they get a lot of cortex, but mostly medial prefrontal. And they found significant improvements on the CAP scale, especially for intrusive memories. They found a corresponding change in heart rate, and again, after triggering people with these scripts. And they found a responder rate of 44% versus 12.5 in their sham. And the drop in heart rate variability and heart rate and skin conductance is shown in these graphs here. And I know there's a lot of small bars, but I didn't have a lot of time to take you through that. Now, I know that Dr. Crystal said that it's exciting about esketamine going through its FDA review, and pretty soon we'll probably be hearing about its approval. Last week, I was at a mock FDA panel for a new TMS device, which will be also before the FDA for a vote in a few weeks. And this is a device for patients with early Alzheimer's. And this device, called NeuroAD, capitalized on the idea that you want to engage the circuitry through various tasks. And in these patients, they're doing a particular task on a screen, like a working memory task, sort of like Lumosity, that game you play. They'll see something or they have to recall something. And the stimulation is actually delivered to 6 different areas of the brain. And each time it moves around to a different area, it corresponds with a different task that would activate those regions and the circuits that feed them. And so this is a large-scale clinical trial. And they had patients with moderate or severe Alzheimer's disease. And what they ran into was that they did not meet their primary outcome measure in the full population, a little bit like the neurogenetic story when they started, but there was a subpopulation of people with milder Alzheimer's disease, and they all had to have an ADAS-Cog of, I think, 20 to get in. And there was a significant finding. And so they're hoping that in a couple of weeks when they take their application to the FDA, that they will get approval, and this will really move TMS into a new space. This treatment takes about an hour, and again, it's a little bit more intensive. The person's got a screen that they're interacting with, and in their sham, they had people just looking at similar images but not actually doing these working memory exercises, and then they had sham stimulation going on. Again, if there was time, there are so many areas where TMS is really, really promising. We've got OCD, depression now. There are actually TMS devices. There's a portable TMS device you can get for migraine, which you throw in your backpack or your handbag, and if you get a migraine aura, you can pull it out, charge it up, and pop a couple pulses into your head to abort migraine. But there are many, many areas of brain function that are being evaluated. Many of these have been in clinical trials already, some of them with very positive clinical trials. There's a large smoking cessation trial that has just finished up and has positive results that are soon to hit the market with one of the BrainsWay H coils. But all of these areas, migraine, multiple sclerosis, traumatic brain injury, pain, Parkinson's, executive function deficits, substance use disorders, schizophrenia, PTSD, OCD, anxiety, and bipolar depression. We have many patients with bipolar depression who want to get TMS, and they come to the clinic and they ask for it. And we don't treat them because it's not approved or covered for these patients. And the reason is that we make them quite manic. And sometimes we make people quite manic with TMS even when they say they aren't bipolar. So we screen very carefully for that. Particularly with high frequency stimulation, it can be quite activating for people. But among these areas of new therapeutic indications are bipolar depression. And this company, BrainsWay, has completed a large-scale clinical trial that did show efficacy after 3 or 4 before it randomized trials did not show efficacy for bipolar depression. It's been a tricky nut to crack because you have to figure out how fast to stimulate to not make people manic, whether or not they should be on concurrent mood stabilizers and anticonvulsant treatments during the sessions. But they were able to differentiate active versus sham over a 6-week course of treatment in a recent clinical trial. Not a huge one, but one with positive outcomes in 50 patients. So they might be on their way to getting the first indication for depression. We completed a study with the regular figure-8 coil in patients who had PTSD, motivated by the idea that when these companies run these large clinical trials for their regulatory pathway, they exclude patients who have PTSD and comorbid OCD and comorbid everything. And in real life, when you're treating patients with treatment-resistant depression, PTSD is a common comorbidity. So we did a study that was at 2 sites, one at the VA and at Butler Hospital, my colleague and I. We were really interested in getting imaging outcomes and EEG outcomes, but we treated with 5 hertz, which is a sort of an intermediate, not too fast, not too slow treatment, which is more anxiolytic, and used EEG F3 targeting, and evaluated both PTSD and depression symptoms. And this is open label, but we were very encouraged to find responder rates in the 48, 50, 65%, depending on what scale you use. And also the depression outcomes were aligned with what we usually see. About 43% responded and 34% remitted. These are patients, many of whom had early life trauma and chronic PTSD, combat veterans who also had very chronic PTSD in addition to meeting criteria for depression. More reflective of the kinds of patients that we really see in our clinical practice. And what was exciting was if the PTSD symptoms got better, the depression symptoms got better. They seemed to move in parallel. Now again, looking at what is going on in the brain when we treat these patients, we are interested in the mechanisms, what changes with TMS, and then what are the predictors? What are the changes that actually go along with getting better? And just for a minute to revisit these networks that in depression and anxiety, which have been particularly relevant. The default mode network, which is independent of tasks when you're just resting and offline, usually staring at a crosshair in the MRI. Central executive network, which is involved in memory processes and goal-directed behavior when you're making decisions. And the salience network, when you're giving your attention to biologically salient things that are going on in the environment and trying to determine whether you should be focused externally or on information such as threat. What we found in the imaging study is that, no surprise, this is probably the case for all responses to all treatments, that people who had healthier network function at baseline had better clinical response. And again, we are looking at these networks in relationship to the subgenual anterior cingulate and bilateral amygdala. And then also that connectivity subgenual anterior cingulate was both a predictor of who got better and a mechanism of response. Again, sort of confirming and replicating some of the work that other groups have done for both depression and the PTSD. So those findings are not just unique to major depression. We also found that uncoupling the hippocampus to the salience network, which is something that you would need to do to not have a fear response to triggers, was important for PTSD improvement. There's an enormous body of imaging studies, and it would take forever to talk about them, but I summarize them here, and the work continues, and it's getting even more elegant over time. First of all, we learned about the way there can be either inhibitory or excitatory effects of stimulation. We've learned about the fact that when you stimulate, you're not just affecting neuronal tissue right underneath the coil, but these other remote regions. And we've noticed that the changes, the behavioral changes, the clinical symptom resolution happens really when you impact some of those more distal regions, not just the one right under the coil. And it does appear that TMS modulates, or maybe I'll dare say normalizes, if you compare normals to depressed people at baseline, some of these functional relationships between those networks I described. What's quite fascinating is that the same imaging changes, particularly around resting connectivity, happen across studies, kind of regardless of whether using high frequency or low frequency and where they're putting the coil and what parameters they're using. But again, these have all been sort of smallish sample size. Back to this question of how TMS works, and the clear answer is we really don't know. There are studies that show it changes blood flow and metabolism at the stimulation site and elsewhere. We know that there's, like other drugs that treat depression, there's upregulation of BDNF, brain-derived neurotrophic factor. We know that there are reductions in GABA and glutamate concentrations. We know that there are changes in synaptic plasticity, that synapses are working more efficiently and signaling in a stronger way. We know that there are changes in neural oscillations, and we get that with EEG data. And we know that there are changes in connectivity, particularly between the prefrontal cortex and anterior cingulate. Building on those, what's inspiring for the future, some of the work surrounds neural oscillations, right? So we all have these oscillations of neuronal activity that can be detected on scalp electrodes like EEG. And if you compare healthy people with depressed people, you see that there are abnormalities between anterior and posterior signaling in the alpha frequency range. That's the 8 to 12 hertz range, 8 to 12 hertz. And so some of the hypotheses about how TMS might work is, well, maybe when you're stimulating, you're entraining these oscillatory rhythms, right? If you stimulate at 10 hertz, you'd entrain right in the middle of that alpha frequency. And in fact, that's been demonstrated with a couple of different sorts of neuromodulation, that you, for a while you're applying stimulation, you entrain these rhythms in particular places, depending on where you are placing your stimulating coil. And one hypothesis is maybe it's like you're sort of resetting these endogenous cortical thalamus pacemakers, and that there's this hypersynchronous pattern of depression, sort of like a cardiac arrhythmia, right? Like you have a tachycardia, and then you come in and you shock it with so many joules and you restore sinus rhythm. Sort of that kind of concept, that maybe what you're doing is in training, and then when you let go, you're restoring some these natural endogenous oscillators. To capitalize that idea, a company called Neosync has made an investigational device which measures your brain's alpha rhythm, does a little single lead EEG in front, and then synchronizes the pulsing of the stimulation so that it matches your own endogenous alpha waves. So if you're 10.5 and you're 9 and somebody else is 12.2, it's going to stimulate at your own and maybe better entrain those rhythms. And this is an interesting concept, and it was studied, the first clinical trial, with a device that has 3 rotating neodymium boron magnets, like buckyballs, those really, really, really strong natural magnets. And they just rotated with motors so that it produced a very weak sinusoidal wave matching your rhythm. And this is an easy study to active in sham, because the sham device just rotated bars of metal that were not magnetic. And this study, it was looked at in a large clinical trial headed up by Andy Luchter, and we were a site in this, and it appeared to get close. It met its primary outcome, but only in the per protocol population. These were 20-minute treatments over 6 weeks. The company, now trying to get to FDA with the first ever take-home device for depression, has taken that mechanism and put it in a little helmet. And now we are just at the end of a large-scale clinical trial, which has enrolled 150 people over a number of sites. The last couple of people are finishing up their last couple weeks of treatment. In my lab, we've done a lot of work with looking at EEG and TMS, and we know that these alpha rhythms don't change. You know, it does appear to be an endogenous signature you carry around with you. Neurodegenerative diseases are characterized by slower alpha frequencies or signatures, but when you treat with TMS, it doesn't seem to change your endogenous alpha signature. So they're hoping with the results of this trial in the next 6 or so months that they have something go with FDA, and this would be a device that we prescribe for our patients to take home and use, and the home use model would be something like a CPAP device or a nebulizer. The patient would go get it at a supply store or something like that after we did the EEG and prescribe the treatments. EEG is a great opportunity to learn about connectivity in the brain and what's going on because it's so quick and easy to put on a cap right there in the clinic before you put the stimulator. We collect data from people's scalps with EEG while we're stimulating, before and after we're stimulating. One of my mentees applied a machine learning algorithm. We had a very, very simple dry electrode cap that you could put on. It had 8 little recording channels, no fuss, no goop, no nothing, just put this cap on, and we collected data from people before and after, before their first TMS and after their last. And it's really, with the computational power that you can bring to EEG, there's an opportunity to find all sorts of signals for new things. We don't always know how to interpret these signals, but it's very exploratory work. But in this one, it was clear that changes in alpha coherence, which coherence is something in this front of the end is wiggling at the same thing something back there is, and so we think they're working together. That some of these coherence changes at the beginning predicted who would get better with significant specificity. And people are interested in using predictors because TMS is a lot of money, a lot of time and effort, and we're interested in finding out who are the good candidates. If we could find that out early on, that would be useful to know. But then it also gives us some opportunity to figure out for the other people what we need to be doing differently. So I'm going to wrap up now. You've been a very patient audience. With some insights. So far we know that it's very safe and very effective. 10 years ago, the International Foundation for Neuropsychophysiologists came out with a seminal paper, Rossi et al., which had the safety guidelines for clinical application of TMS therapy. And there were guidelines here. You should stimulate more than this intensity, and the trains should be this short, and the intervals between them need to be this long. And the group convened again, and I was honored and delighted to be invited to be a co-author this time to revise the Rossi safety criteria. And now, after 2 million treatments have been delivered, the seizure rate is so low that we can no longer identify seizure as a risk associated with standard treatment to dorsolateral prefrontal cortex. If you stick a coil right on your motor strip and crank it up high enough, you can get a seizure, as Dr. Lisenby told you, but it really does appear to be quite safe. We know that we can treat depression now more quickly, and we can target different areas of the brain. We wish we knew exactly where to go in each person, and there's some very elegant work going on to try to pin that down. We can now treat OCD, which is exciting. We can now treat for 3 minutes with a theta burst protocol and have equal outcomes. We know some things about the functional connections that are changing, and there's preliminary data for a number of neuropsychiatric disorders. I would convince you TMS is not going away, and we'll continue to expand as we learn how to use it in more neuropsychiatric disorders. I think, though, in the future, because it is expensive, time-consuming, and all the rest, that some of these imaging and EEG biomarkers will help us figure out how best to apply it. Where in the brain, how fast, how many times a day, all these sorts of questions. Individual patient EEG signatures will maybe eventually guide us in what parameters to apply. Figuring out how to do symptom provocation and extinguishing particular symptoms like anxiety symptoms, or cognitively enhancing people with stimulation together with other endogenous neural activity is going to be a big focus for this area of work. I think just doing this work has given us some understanding about mechanisms of action. Maybe they're specific to TMS, maybe they're broadly applied to depression. But I think one of the big areas that we'll have to work on is how to sustain response. We can get about 50% or more of people better, and then keeping them better over time is a real challenge. I just got a little grant to use ecological momentary assessment, which is an app you would have on your phone, and after you get it better from TMS, it would ping you once a week to answer some questions and collect some data from you, and hopefully we can individually customize when you need to bring somebody back in and reintroduce to treatment and top off so that they continue to stay well. At this point, your insurance will pay for you to get TMS if you have severe depression, and then you go away, and we know that over the course of a year, about a third of people will start to slip after they get better. We do know that if you retreat them with TMS, about 90% will pop right back into remission. So what we'd like to do is be able to not wait till you're all the way sick again with your depression, but catch you when you're slipping and be able to top up and keep people better over time. But that seems to be a very individualized thing. Some people will go years, some people go months. So figuring out that piece is going to be important. And again, improving access so that people can have take-home devices, either for maintenance or even to use in other contexts, is a very exciting area. So I'll wrap up there and take any questions. I thank you for your patience and interest today.